Okay, anyhow, you can see my screen, I guess. So I will start. So last time we discussed about the source filter theory. The source filter theory, that is what we discussed about source filter theory. And what did we find? That there is a excitation signal. It's a train of impulses or random noise. And then it goes to a system. System has a glottal system, vocal tract resonances, lip radiation. It's a complete, we can club them together as a, let's say, a voice production system. We can club them together, and finally output is your speed signal. That is what we went through. So there is a source excitation, voiced and unvoiced, two types of, and then it passes through a system which we call filter, and the result is our speech signal, whether voiced or unvoiced. So now, how was the system? What did we find? That the system was like this. If we go through in time domain, we'll get convolution. In frequency domain, we'll get this glottal model, as I said, vocal tract model and lip radiation. And this is your total transfer function, so to say. Total transfer function of the system or filter. And what did we get? We saw that this is like two real poles. It's a low pass filter. 1 by 1 minus a z inverse whole square of multiplicity 2, where a is very close to 1. Lip radiation is again 1 minus bz inverse, where b is very close to 1. This is the part. And vocal tract system is resonators, so conjugate poles, pairs of complex conjugate poles you have generally near the unit circle. And the closer you are to the unit circle, the stronger the resonance. The farther you are, the weaker the resonance. And then you can express that in polynomial form. Finally, you have all this. If you club all this together, this is what you get. Or voice speech, an unvoiced speech, same thing you will get, more or less. So it's a polynomial of z below, and this is your impulse excitation, or this is excitation signal, whether it be impulse or random noise, and this is your speed signal, and this is the transfer function. And this is, you can also say, it's z equal to this. So the entire thing now we were expressing as Ez, and then you get Sz. Now our goal is to find, see, we'll in this lecture, for convenience, you'll understand why. We'll, instead of using this Ez, we'll use Uz. There is a reason why, but only for notational convenience. Okay, as we discussed LP analysis, today we will discuss about linear prediction analysis. There we will have an error term. An error is generally denoted by E or En, and so we'll have Ez term coming up there. So to avoid ambiguity, we will use this Uz from now on in this lecture. Okay, so finally this a term that we were saying previously, this you can just represent by it's a gain term, some value, positive number. It's a gain, whether it is voiced or unvoiced, and we have a polynomial of some order p. And another thing we'll do is see this plus. You can also write this as a k z inverse k. There is nothing special about writing plus. You can represent this one. For example, if this was a k dash j or minus k, you can write a k equal to minus a k dash. So this will also make our analysis slightly easier. It will help us compare what we want to do. So what we'll do is we'll represent finally. Let me go back. So we'll finally represent our 8z is sz by uz. We are using uz in the source filter theory so that we do not have ambiguity when we discuss linear prediction analysis. Today we'll discuss about linear prediction analysis, but just recapping what the source filter theory is. But this is what we will use, and what do we get? We get a gain term. Previously, we used to represent this by a means gain for voice speech or gain for unvoiced speech, but it's a term, basically a constant factor, constant scalar, and then we have where k equal to 1. It depends upon how many poles you have modeled in the how many resonators you are modeling in your vocal tract. Based on that, this basically number comes up. So k equal to 1 to some p, we'll say some p, some p. That calculation you will have to do. So if you are modeling, let's say, four resonators, you think that there are four resonances in your speech signal, let's say 8 kilohertz speech signal. That means your maximum frequency is 4 kilohertz, and you are saying that every kilohertz, as I have said, we have found in studies have been done that more or less every kilohertz there is a resonator for voice speech at least. So that means two poles, you get 8. That means you get this value. There will be 8 poles there, 2 poles per resonator. So likewise, you can have a rough estimate of how what should be the number of poles. So that is how we represent the transfer function of the source filter theory. So now, so we have this equation. Now, if we see what this equation means, so if we just so sz equal to s of z, so sz minus, sorry, sorry, sz minus summation of ak z to the minus k sz equal to g of uz. Okay, so if you put it in, convert this thing into time domain, what will be Sn? Simple properties. S of n minus k. This is S, G of un. In other words, Sn G of un. So look at this. equation. Okay, look at this equation. S of yes, so this is the equation we wrote. S of n, if your model, if you think there are p poles in your system transfer function, so that p comes here, and this is the equation. So if you have now, let's say, so what you are basically saying is, if you have a signal, let's say speech signal, something like this, you take this is a chunk of a speech signal, a frame of a speech signal. Okay, so this speech signal, how was it produced? It was produced by a filter, HZ or HN, whatever, and there was a train of impulses, periodic train of impulses, which we'll call UN here. So, so this train of impulses, as you see, let's say n equal to 0, n equal to p, n equal to 2p, or you can say whatever notation, n naught, 2 n naught, up to you. This is your pitch or fundamental period or pitch period. Okay, so what the equation is saying, this equation, sorry, this equation, what it is saying is, see, un only at certain points there is a unit value. Other places, this un is 0, the excitation is 0. So what happens is our equation comes up as Sn so if this is your n in the this is your n, the times axis is n. So here, let's say this point S of n is a summation of weighted sum. You can represent this as weighted sum of previous one p samples. See, previous p samples, you can represent this as a weighted sum. Any sample, any current sample n, you can represent it as a weighted sum of previous p samples. When you have this n coinciding with the excitation impulse, then there will be another term which will come, a g term will come. The gu and un is all one, a g term will come. When the impulse, when n is the impulse sample, this sample, then there will be another term g. You can represent as speech signal as previous sum of weighted sum of previous samples plus another term g will come. But when there is no, when it is not coinciding with the impulse, then any speech signal, any speech sample can be considered as weighted sum of its previous samples. This is the basis of linear prediction analysis. This is the basic of linear prediction analysis. There are two words, linear and prediction. So you can predict the value of a current speech sample. You can predict, this is a prediction. So you can predict, estimate the value of your current speech sample from, how will you predict? With a linear combination. Linear combination is weighted sum. You know what is linearity, what is a linear operation. Weighted sum of is previous, sorry, n minus k, its previous samples. So it's a linear operation, a linear sum of its previous samples. Any current, the value of the speech signal at any time instant, any sample instant, at any index, you can calculate from its values at previous indices or previous times. This is the this is called linear prediction. This is a technique of field of signal processing. It's called adaptive signal processing. But so now this technique exists now, and we have seen from the source filter theory, what we are seeing from the source filter theory, that the speech signal, that from that models, the source filter theory, whatever we get, it already has, that model has this property. So can we use linear prediction to estimate what will be the values of AK? So from the source filter theory, we already get that we can represent the speech signal as plus GUN. So is there any way now to estimate the values of AK? If we can estimate the values of AK, then basically we have found the parameters of the model. We have basically found what our transfer function of the vocal tract system is. There is a big achievement, means we have found the internal mechanism, we have described the internal mechanism through which the speech is produced. So this is the basis of linear prediction. The source filter theory allows us to model the speech signal like this, and when there are no impulse, so in between the impulse train, in between the impulses we have, so this term becomes zero, and the speech signal is simply a combination of its previous samples. The solution to find what are the weights, individual weights given to the samples, previous samples, how to find out, that technique is called linear prediction. So linear prediction is one of the most powerful speech analysis techniques, and so this allows us, you can obviously see, if we can estimate those parameters, the AK, the poles basically, then we have basically resolved the entire system. We can find, determine what the vocal tract, how it is. So we can plot the spectrum of the vocal tract. We can plot, if we can find the formants, and so on and so forth. And you will also find during this analysis we get another way. We saw last time that autocorrelation function can be used, but if you are able to find out the transfer function of the system, it allows us a simple method to determine the pitch from what is known as LP residual, from a signal called LP residual. It comes as a byproduct of a linear prediction analysis, or popularly known as LP analysis of speech. Linear prediction analysis of speech. So let's go now to our slides. So we have talked about all this. So how to find out the parameters? That's the question. Let's find out the parameters of this model. So we will say any speech sample at any point n, as I have said, will represent it as a weighted sum, as a linear combination of p previous samples. The weights are given by alpha k. We hope from this linear prediction analysis, we hope that this alpha k becomes equal to ak. Means then we have basically achieved, we have truly represented the uh, speech signal. That is our hope. So so what will be error? So error will be if you have predicted this, this is your prediction, your current value is weights of previous. Okay, and so your error is your true value is this, but your predicted is this one as hat n. So this is your error. So now we will use mean square. We'll take a mean square of this error and try to minimize the error. What we want to do is we have this signal. We already know the true value. We have a frame. The speech signal, we took a frame of this. We already know each and every value what it is. But we are saying that this value is a sum of these previous values, weighted sum. And we am calling them as hat n. And already we know the true value. So let's say this is of length n. The frame that we took, it has n samples. So your error is this. We want to minimize this. If we are able to minimize this, there the with respect to what? The mean square error will be 1 by n. So this will be your mean square error. Square, and we have taken mean. This serves no purpose. For a, we will do frame by frame analysis. All the frames will be of the same length, and this is a constant. You can remove this. There is no benefit in putting this constant value. So E square n. So for each sample, we are measuring the error. And we want to minimize this error. We have to minimize this mean square error. We call it, we denote it as E. We have to minimize this error with respect to what? With respect to all the coefficients. With respect to all these coefficients. With respect to all these coefficients. We want to minimize this function, this energy function, this energy term with respect to all these coefficients, and that will give us the values, that value of these coefficients or weights. So let's go about this then. How will we go about it? Let's come back. Yes. Yeah. So we have, this is the term we said, En. We have to minimize this. So we'll do, you know how any function, primary, you have a calculus, you already know this basic calculus, that the minima of a function, it's determined by the derivative, wherever the derivative is 0, that basic calculus, you know. So we'll use this basic calculus. So we want to minimize energy, this partial differential This is a partial differential equation. Okay, with respect to this particular term, we are denoting it at alpha I. You can denote it by alpha k. It doesn't matter. These are all notations. So, how many parameters we had chosen? We had chosen p weights or p coefficients or p poles. So let's now see what happens. So E was your summation I equal to 1 to n E square n. So del E by del alpha I equal to be 2En del En by del alpha I. And what is En? En is again, you know, Sn minus summation of Sn minus summation of S of n minus S of n minus, sorry, En equal to Sn minus summation of alpha k S of n minus k. So if you differentiate this term En with respect to some alpha I, you will get this. You will only get this S of n minus I. The minus term is here. And this is nothing but your twice En. Now you rearrange the terms. 2 is not needed. It's 0. You have to equate it to 0. Forget about the 2. So just simplify Sn minus 1 n minus I Sn minus I minus of this term that you have. So two summations n equal to 1 to n, it comes, and k equal to 1 to p. So you get this term. So you can just rearrange. During simplification, you can rearrange this term. It's a simple property of mathematics. Okay, you can rearrange this term. So you put k equal to 1 to p as the outer summation, and obviously alpha k will come because the variable k is now pulled out. You can even put Sn minus k here, but there is a reason why we are not doing that. And then you have, because it will see, it will make our analysis simple. And you have this outer summation, we put it on the inside. So you have this. So finally, what you get is you have equated this term with the multiplicative term. A weight, there you have the weight and a multiplicative term and a simple multiplicative term of the samples. These are simple mathematics you have done. Now the important point here is we talked about autocorrelation function. What is autocorrelation function? From Rm whatever is your length of your signal, length of the speech frame, S of n minus m or S of n plus m, does not matter, you can put anything, S of n plus m or n minus m, because R of m equal to r of minus m. You can find it out for any finite length signal, which we can consider it as deterministic. This is going to happen. So whether the lag is positive or negative does not matter. We will give the same result. It is symmetric function. So anyhow, so let's take this definition. So this is our autocorrelation. So what will have? What do you see here? S of n, S of n minus I. This is nothing but R of I is the autocorrelation function. Similarly, from that same definition, if you think about it, just two steps you can do it on your own. This you can say R of k minus I or I minus k, does not matter. Let's put k minus I. Actually, you can put a modulus here, but let's for convenience that just let's say k minus I. Okay, so rk minus I, this term, and this is ri. So your whole analysis, your whole equation now becomes very simplified. So your set of equations that del E by del alpha I equal to 0, from that where I equal to 1 to P, from that you get this equation, this set of equations. So now let's do one thing. This equation we have got. Let's see, let's expand this equation. So k equal to 1 to P. So k equal to 1, alpha 1. Let's take I equal to, let's take here, this is for I equal to 1. Let's take for I equal to 1. So I equal to 1. So k, when it becomes 1, alpha 1 R0 plus k equal to 2 means alpha 2 R1, alpha 3 R2. Like this it will go. Finally you get k equal to P, alpha P R P minus 1. And what do you get here? R1, because I equal to 1. Similarly, let's see for I equal to 2 what happens. You have alpha 1, because k equal to 1. We have now putting I equal to 2. Okay. So alpha 1 R1, alpha 2 R0, alpha 3 R1, and dot for alpha P minus 2. Likewise, you continue for I equal to 3, and this is finally for I equal to P. So this is a set of linear equations. For simple equations, you might have remembered in mathematics, you can use this Kramer's rule and all that. But there are, if you have one or two equations, but there are so many equations here, you don't use Kramer's rule and so on and so forth. We'll use some other methods for this purpose. But let's put all this in matrix form that you will understand now. So you have this set of equations. All this entire set of equations, you can put it like this. So R naught alpha 1 plus R1 alpha 2 plus R2 alpha 3 dot RP minus 1 alpha P. The next, I hope you know this simple matrix multiplication. So this simple matrix multiplication, you can put this in a matrix form. So this is a standard equation. You must remember AX equal to B. So what will be X equal to A inverse B if inverse exists? So we can also solve this. So we can say this is a let's see how the denominator. Yeah, so we can write this as R. This matrix we can denote this as R. We are denoting by uh, a vector as with a dash or underline underscore below, and we can even denote this as R, a matrix R multiplied by a vector resulting in another vector. So what will be the alpha equal to R inverse R. So this is the result. Now this result is the inverse, the calculation of inverse is not a small thing. We take it for granted, but the calculation of inverse has a lot of calculations involved. So instead of this, so we can utilize this particular structure of this R, this matrix, and we can derive, we can find the solution without taking the inverse. So one of those popular solutions is given by something called the Levinson Dublin algorithm. Levinson Durbin algorithm. And why is it possible? Because you see R. You see the structure of R. The structure of R is like R0, R1, P minus 1. So there is a structure. This type of structure, this is a symmetric matrix. You can see, okay, it's a symmetric matrix. So R equal to R transpose. And its diagonal has the same value. Diagonal has the same value. This type of matrix is called a Toeplitz matrix. And because of this particular structure, you can derive, you can develop some techniques which to find solutions without taking inverse. One of those techniques, one of those ways is this Levinson Dublin algorithm. So let's see now how to use the Levinson Dublin algorithm. So Levinson Durbin's algorithm. So this is the set of, this is the algorithm. This is the method by which you can find those LP coefficients without taking inverse. So there's a set of there is a set of equations that has to be followed in an iterative manner. So let's see this using an example how this is done. Okay, let's imagine this. There is a equation just, so you decided P equal to 2. There is only let's say only one resonator there, something like that. Okay, P equal to 2. So I equal to 1 and 2. This is the structure of the this is the Toeplitz matrix. This is the set of equations that you get, alpha I equal to 0 when you set when you try to minimize the mean square error. So what does the Durbin method say? Let's see. First, step number 1. This is your I. This is now your iteration. I now becomes iteration, and this iteration will continue 1 to p to the number of, the iteration will continue 1 to p means till the number of your coefficients, number of parameters you have to find out. Okay, so this is iteration. First iteration, you see, set E not equal to R0. R0 basically energy of the speech frame. Then for I equal to 1, you can only calculate for that. Let's calculate K1. What does the equation say? So R1 minus j equal to 1 to 0. So obviously j equal to 1 to 0 is not going to be possible. So for I equal to 1, this term does not exist. Okay, so R1 divided by E0 for K1. So K1 will become R1 divided by E0. So we got R1 divided by E0. E0 means R0 in our case. Now next, so alpha 1. So alpha 1 for the first iteration. Okay, so now let's say alpha 1 for the first iteration. Okay, alpha 1 1 will become K1. Now alpha, you see this, you can also have alpha 1 1, alpha 1 0, but alpha 1 0 is not there, so this equation you cannot use in the first iteration. Only in the second iteration, from the second iteration you will be able to use this part of the equation. So in the first iteration now, so E of 1 1 minus K1 square, E of 0. So E of 1, you get 1 minus Ki square, E of 0. So 1 minus K1 square, E of 0. So if you plug in all these values, it comes out like this. Now the second iteration. And remember, the iteration will continue till the number of coefficients are there. So K2. So K2 will come. So for K2, R2 minus, see, J equal to 2 minus 1, J equal to 1. That means you can use this now. For I equal to 2, you can use this. This term is also valid. This term also comes into picture. K equal to 2, R of 2 minus J equal to 1 to 1. That means J equal to 1 minus alpha 1 1 and R of I is 2, J. So from that, you have all this. R of 1 you can definitely, you already have. Alpha 1 1 you found in the first.
Sir, you are not audible, sir. No, sir.
Now I have to redo all this because of network issues. I think you can see the screen.
Yes, sir.
Okay. So the Dublin's algorithm I was going through an example. So now k equal to 2. Oh, sorry, yes. I equal to 2. So alpha I. So alpha 2 2 equal to k2. And then here, now you will see alpha 1 you can even put. Yeah, alpha 1 for the second iteration equal to alpha 1. So alpha 1 for the second iteration equal to alpha 1 for the first iteration we got minus k2 that we already derived previously, and alpha I is 2. This is the equation that comes. So from that, if you simplify, it comes as this equation. That's it, because the equation you got basically. So alpha 1 2, which is after the second iteration, after all the iterations, whatever your coefficients result, those are the final coefficients. So if your iterations will run from I equal to 1 2 3 4 p, so alpha 1 p and alpha pp, these are your final, these will be your final solution. So this is what is your alpha 1 to alpha p will be. It is a simple example, but these are your steps. These are your steps of the Durbin's algorithm, and with this, you can, without taking inverse, you can use the properties of the Toplius matrix to get the solution for LP analysis. So what I will do, I will take a break. Okay, I will give you some 10 minutes break, then we'll resume. Okay, we will give 10 minutes break and then we will resume for our next class. So we'll meet at 11:05. Yes, so let's start, resume, sorry. So we have, found through the Levinson doubling Durbin algorithm the coefficients alpha k in linear prediction analysis, for linear prediction analysis of speech, of a speech frame, rather of a speech frame. So let's see how, why we, let's see what the source filter theory says and what we are trying to do. So according to the source filter theory, so we have an excitation signal. This is your source filter theory, you have an excitation signal, and the result is your speech signal SN. So this is the transfer function that we have talked many times now. So you can represent the transfer function in a block diagram in a control systems. I am sure you have you know these basic control systems, how you represent transfer functions of a system in block diagram format. So this is how it is. And what we are saying is, we found that we are trying to now. So we are saying that we have escape of n equal to summation of s of n minus k, where k equal to 1 to p. So, and we have this error, and the result is error which we want to make it 0, Sn minus S square of n. So you can represent all this. This is Ez. It will come out to be, if you represent, this is what it will come out to be. So if you input the speech signal, if you have the speech signal, and then you put it through this linear prediction, we call it the linear predictor filter, you will get an error signal En, which we want to be same as this signal. If we are somehow, if the linear prediction analysis, LP analysis is correct, that means your alpha k becomes equal to your AK, then you will find whatever error signal you are getting will be exactly equal to your excitation signal. Then your source filter theory, we can verify, it's like a verification of the source filter theory. So let's see what happens. This is what I am saying. So if you take this as a total system, if you find out this is SZ, then uh, this is EZ, then that is why I changed the nomenclature of from En to E1 in the source filter theory, because it helps us in analysis. So basically, if you have alpha k equal to AK, we are truly able to find out the true parameters of the system. Then your En, the error signal, will be same as this train of impulses or a noise train of impulses or your random noise. So let's see what happens then. Let's see how LP analysis results, what happens to LP analysis results. So we went through all this. Let's see some of LP analysis results. So this is a frame we have taken. This is a frame. It's a frame size of 20 millisecond. It's a 10 kilohertz sampling rate, so its maximum frequency is 5 kilohertz. This is a digital speech signal of maximum frequency, Nyquist frequency 5 kilohertz, and hence 10 kilohertz is the sampling rate. So we obviously, from the speech signal, we don't know beforehand what are the number of vocal track resonators that are there. What is the true nature of the vocal track system transfer function? We don't know. So we generally think that every what is called every 1 kilohertz there is a resonator. That means two poles. So we'll need a cascade of resonators. So here, let's say if we assume 5 resonators, there are there. So 10 poles plus this 4 poles. They are given because to predict if there is slope. Some real poles, if you have, there is a decaying slope or increasing. It's increasing or decreasing trend. We have talked about it. So anyhow, so based on this p equal to 14 is a kind of heuristic. It's kind of heuristic value that we have found good results with this number. So the general trend is like, if you have R resonators, then you will have 2R poles and plus a few real poles. It will be complex conjugate poles, and for plus few 2 to 4 real poles you will add. This will give you a number of parameters. Basically, that's a heuristic rule kind of. So based on that, p equal to 14 has been chosen, and let's see what happens. So we got through Levinson Durbin's algorithm our coefficients. So we got your Sn minus alpha ks of n minus k. All these coefficients we got. This 14 of them, k equal to 1 to p. So now, sorry, this is s cap n, s hat n or s hat n. So this is en. Sorry, this is the energy. So you can calculate what was your energy. Sorry, not energy, error. So this is your error signal. This error signal, you see, there is a very interesting properties. So you can see here, this is a periodic voiced waveform. It is it is repeating. This sequence is repeating. This is a periodicity. You can see there is a repetition vector. Just short voice waveform, voice sound, but it has periodic properties. Not purely periodic. We call it quasi-periodic, but you can see that. So here you see these locations. There is a sharp spike. In the rest, it has got very small values. It is a noisy signal, but still it looks like a noise waveform, but still you can see some very strong spikes at certain positions. These are, as we said, if we are correctly able to estimate our LP coefficient UN, so we should have got something purely like these zeros and impulses, but obviously in reality that does not happen. But you can see in these positions large values are we are getting, and the rest of it is in the vicinity, it is having less smaller values. So this is, hence this error signal is a very important method. Using this error signal, people predict or estimate the pitch of the signal. So this helps in this residual signal. This is called, also called LP residual. This error signal is also called LP residual. This residual signal helps in estimating the pitch of the pitch or fundamental frequency or fundamental period of the signal. Now, if you because you have this alpha k, now we assume that the alpha k is truly representing our vocal tract. Okay, so alpha k, we assume that alpha k is truly representing the vocal tract. Then what will we have? We'll have this 8z. We got some g1 minus. Let's forget about g for a moment. Okay, let's this alpha. This is we model it in source filter theory as a, we say ak. We hope that alpha k is nearly equal to exactly equal to ak. Ak is e to the power minus k. That's it. That's what it is. So obviously z equal to e to the power j omega. If you put, you get the transfer function, this frequency domain, the magnitude spectrum of the system. Now, if you plot the magnitude spectrum of the system, this is what it looks like. See this? You see this line? So this zigzag is the spectrum, log magnitude spectrum of the speech signal, and this line you can see here. This is from h of e j omega magnitude 20 log. That is what we are plotting. You can see providing the it is providing the what you call the spectral envelope of the speech signal, and from this LPC spectrum or the estimate of the vocal tract system, estimate of the voice production system. In fact, you can see these areas there are peaks. So this log magnitude spectrum obtained from LP analysis. This also helps in estimating the formants of the focal tract resonances. At what frequencies those focal tract resonances are occurring. You can see here, for example, there is a peak F1, this will be F2, maybe this will be F3, is small, maybe F2, F3, F4, F5. So LP analysis helps in estimating your excitation source. You can see large values at which the system was excited, the vocal folds were vibrating, that we can we can model this as a train of impulses. And we also get the spectral envelope from LP analysis, which allows us to find the vocal tract resonances. And the last one, this is nothing but En, e to the power j omega, basically. What is the spectrum of the error signal? Obviously, it is more or less like a noisy signal, and noise, it's a white noise. It has a flat spectrum. So this is not a very significant. This does not have much significance, but this LP residual or pitch estimation and this vocal tract or voice production and the spectral envelope that you get from LP analysis, that helps in estimating the formants. Yeah, so now let's talk about this parameter, this P I have talked about. It's like a heuristic thing, uh, means based on lots of analysis. People have tried and tested trials, basically, lots of trials and errors. Heuristics means lots of trials and errors, trial and errors. You find out, okay, this seems to be the value that works for us. So here is a speech signal. It's and we have this. It's short time Fourier transform, and we are changing the value of p here to see what happens. If you have p too low, see your formants are not represented properly. Only one it is shown. Correct. It's not, position is not correct. If you have now, if you increase, I think here it equal to, this is p equal to 4, is p equal to 8. You see, you can see F1, F2, F3, it looks more reasonable. It also matches with the spectrum of the signal to a certain extent. If you increase this p to 12, again it's okay, and then it seems even more reasonable. It seems there are too small F3 instead of this one was probably incorrect. This one is probably more correct. F3, F4, F1, F2. These are these, as you know, in voice speech, the lower, higher frequency resonators are weak. But if you keep increasing, now this dubious, this incorrect, all this in the LP spectrum, you will get all this incorrect, false resonant peaks will occur. P equal to 16, P equal to 20. You can see the false resonances will occur. So in general, the decent means the acceptable heuristical rule is, as I have said, if you consider a 4 kilohertz speech signal, every kilohertz there are around there is one resonance that is occurring. That is, in case of voice speech, that is more or less established. In case of unvoiced, it is not very established. We don't know very certainly. But in case of voice speech, it's a general good rule to assume that every 1 kilohertz there will be a resonator. So for 4 kilohertz there will be 8 the number of resonators. So if it is R, so number of parameters in the LP model, or indirectly the number of poles that are there, it will be 2R. Plus you add a few more poles, because you see the spectrum, what happens is it is a decaying spectrum in case of voice sounds, or in case of unvoiced is an increasing spectrum. That means there is some real poles there. And you know what happens in real poles we discussed. It gives an increasing and decreasing trend. So, on top of that, 2 to 4 additional real poles. This is probably if there is a 3 kilohertz, it is saying maybe it's a 4 kilohertz signaling. So they are considered. So this is around the number that people find uh, useful in getting a correct LP analysis. So this is what, yeah. So now the another thing. Now we got the error signal at every point after LP analysis. Obviously, what is the RMS or mean square error? E equal to, that's all the points you get, n equal to 1 to n. Now, if you plot this average error for that segment as a function of LP coefficients, you will find in general, see, the error decreases. Does not mean you will get the correct vocal rec resonance structure or anything, but what does this mean? As number p increases, that means what you are saying, that you are estimating the signal with a large number of samples, previous samples. So your current sample estimate, if you increase p, just keep increasing p, it is affected by a large number of previous samples. So if you take more, indirectly you are taking more data for estimation. So in that case, you will always find that your error will decrease. You see the error is decreasing as you increase the number of coefficients. But that does not mean the error will that your analysis will give you correct results, because you saw that the vocal rec resonances, spurious vocal rec resonances are coming up. But nevertheless, the point here is, in case of voice speech, you see the error is far lesser than in case of unvoiced speech. That is because we saw in case of voice speech or LP residual, it works better in case of LP analysis. It works better for voice speech than for unvoiced speech. The source filter theory is also more well established, you can say, for voice speech. You have a train of impulses, and then you have the entire transfer function, you get a voice sound. On the other hand, unvoiced speech, if you see, there is a random noise you take as excitation signal, and that comes out. The output is also obviously a random noise like signal, zigzag. But these are the few things you need to know about the pros and cons and of LP analysis. So let's now go to reflection coefficients. So this LP analysis is very useful, as you can see. You can use it for coding, means instead of for a particular speech segment, speech frame, only using a few parameters. Basically, if you have the LP residual, if you estimate the pitch period from that, and if you have your alpha k, the coefficients, and they are accurate, let's say they are accurate in representing the signal, then you need only say 10 to 14 parameters, and this your pitch is another 15 parameters. You have your, let's say, 8 kilohertz pitch signal, means one frame, let's say 20 millisecond. That means I think 160 samples are there, and instead of coding all that. You can store that information that with only 15. So this is very useful for speech coding as well. So anyhow, we are talking about reflection coefficients. So there is a something called reflection coefficients which are used for estimating the area of the source filter, the tubes of the source filter theory model. So what happens is these reflection coefficients, they are related to the Levinson-Durbin's algorithm. What we got this Ki are also known as um, Parkour coefficients. Does not matter. But from the Ki, there is a relation between reflection coefficients and the coefficients that the Ki coefficients that we get in the Levinson-Dublin algorithm. And how are they related? They are related by this simple. It is the negative of the other. So let's see what reflection coefficients first actually mean. So we model the vocal tract system as tubes of concatenated tubes of different cross-sectional area. So in electromagnetic theory and waveguides, if some of you can recall, you will find that if your area is the same, if one tube is there, its area is the second next tube has a different area, then there will be some reflection, electromagnetic wave reflection occurs. Similarly, our function and so on and so forth. But if it is the same, basically there is an extension of the same tube, then there is no reflection. So if Ki, let's say this is 1 plus Ri by 1 minus Ri, Ai basically. If I am wrong. Oh, sorry. Let's do this way. So this reflection coefficient between two tubes with cross-sectional area Ai and Ai plus 1, this is given by this equation. When the cross-sectional area of both are same, it's like an extension of the same tube, the reflection coefficient is 0. So it gives how much energy is reflected back at the junction. Obviously, it's like an extension. Otherwise, when the areas are different, the amount of energy that is reflected back. So these reflection coefficients that we can estimate or which are related to the Levinson-Durbin's Ki parameters, those help us give a relation between the tubes, the cross-sectional area of the tubes. So this is another fallout of the LP analysis, another advantage of the LP analysis. For a particular sound, you can analyze, basically, you can estimate the vocal tract structure as a concatenation of tubes, and you can find out the relative variation of the cross-sectional area of the tubes. So this is another advantage of LP analysis. So let's do one thing. There's a lot of things that we have covered. I could start another topic, but let's not do that, I guess. So let's go back to let's recapitulate what we discussed in this lecture. We have from source filter theory, recap of everything. We had from source filter theory that I will call it UN instead of EN. You get an excitation signal or a which is a train of impulses or a random noise. You give it, you pass it through. One is a glottal pulse model, then vocal rack system, lip radiation, all of which you can club together as a voice production system transfer function, and you get your speech signal. This is the source filter theory. Now, obviously, there are some differences in unvoiced speech. GZ does not play a role. You can put it as one, and so on and so forth. Some small differences are there. But this is overall an system. So, and this system, you can say some gain, some constant gain, the 1 minus ak z to the power minus k. This is the system transfer function, how it comes out to be. So if you analyze this source filter theory model, then you have this you have this equation which says that the signal at a particular time index, actually you can represent in terms of previous its values at previous indices we multiplied by some weights. And and why is that so? Because g of un, it will be zero for most of the time, except at certain points, certain time indices where the impulse occurs, where the glottal vibration occurs. Most of the time it will be zero. Only on those instances where we say the glottal vibration, the periodic vibration we have to model, only that times we represent it with a unit impulse. Rest of the time it is zero. So we see that there is a the speech signal, we can model it in terms of, or it is related with its past, whatever the past samples. And this gives an way of finding out all these coefficients which are indirectly related to the poles of the system transfer function. So here comes then our, that's why then we go for, then because of this source filter theory formulation, we go for LP analysis, which is a technique in adaptive signal processing, which allows us to model any signal at a particular time as a combination of its previous samples, weighted combination of the. This is the formulation of LP analysis. And LP analysis allows us to find those weights. In source filter theory, we also see that the source filter theory is, the model is like that, that we can represent the speech signal in terms of its previous samples. And LP analysis fits into that model perfectly. So we go for LP analysis. LP analysis, we do a mean square error, evaluate the mean square error. And the mean square error, we want to minimize the mean square error. We want to minimize the mean square error. Ideally, it should be zero, but but that's what we want. But if we get the perfect zero, we'll be able to absolutely perfectly able to replicate the source filter theory model. But uh, our objective is to minimize the mean square error. So with respect to these coefficients that we have. So from this, we get a set of equations, linear equations, which comes out in the form of a matrix. A set of linear equations which comes out in the form of a matrix. So this, of course, depending on how many parameters you have chosen in your linear prediction analysis, this is not a you can solve it by inverse, but inverse is a very computationally intensive operation, taking an inverse. So for matrices which are having this Toeplitz structure, which are symmetric and the diagonal has the same value, we have some simple or more efficient algorithms which are not computationally intensive, and one of them is Levinson Durbin's algorithm. So via Levinson Durbin's algorithm, we are able to find alpha, the parameters of the LP analysis model, LP analysis. Once we find that, then we can find out, basically we can estimate our envelope of the spectrum, speech spectrum. We also get the LP residual, which ideally will be exactly like the perfect excitation signal. We don't get it, but we get a very good representation of that. We can use it for pitch or fundamental period or fundamental frequency estimation. We can use this for formant or vocal tract resonance estimation. On top of that, this in Levinson Dublin's algorithm, in the process we have a parameter ki, which are called Parkour. The Parkour coefficients are related to the reflection coefficients in waveguides, kind of the source filter theory vocal tract model, where the vocal tract system is a concatenation of tubes of different cross-sectional areas. So once you know the reflection coefficients, you can estimate how the cross-sectional area is varying from one tube to another. But these are the various fallouts, various advantages of LP analysis, and why LP analysis is one of the most important techniques in speech processing.